Welcome back, folks. In my last video in the series entitled NixOS number 83, NixOS as a music production system, I got PipeWire and Musenix set up for generic low latency recording and monitoring, and I got Ardour and Audacity working with some plugins. This is the second video in the series where we'll dive a little bit deeper into Pro Audio on NixOS by further optimizing monitoring latency and trying to ensure that we get the fewest number of X runs. These are errors that happen when our audio hardware can't feed our software fast enough. To do so, I'll be using a script named RTCQS. I'll be changing Musenix RTIRQ config. I'll be disusing the low latency kernel that I configured in the last video. I'll be measuring sound card hardware latency and adding programs called Plumber and XRunCounter. For this video, I'm going to start out in a place that is close to where I left off in the last video in the series. In that video, I used a virtual machine, so I couldn't really demonstrate what performance and monitoring latency was like in the real world. But in this video, I'll be configuring NixOS on real hardware. And this is a Dell Optiplex 3070 Micro, small form factor desktop. It's a 4-year-old 6-core, 2.2 gigahertz Intel i5 9500T with 32 gigs of RAM. It gets scores of about 1300 single core and 4600 multi-core on Geekbench 6. You can buy one today on eBay for about $130. So there is a newish Musenix feature. At least it's new since my last video. And it provides access to a script named RTCQS. RTCQS is a script that analyzes your system configuration and offers suggestions about potential changes that could be made. Edit wherever you have your Musenix stuff in your configuration. Say musenix.rtcqs enable equal true. You may need to update your Musenix stuff in order for this to work. Once you've enabled it and you rebuild your system, you should then be able to run it via RTCQS like that with no arguments. And it will warn you about things that it's found that are suboptimal. In my case, I have most of the stuff that it goes after already ameliorated. It's telling me that my CPU frequency scaling is not set to performance and tells me how to fix it sort of interactively. I've been having problems making this stick on reboot. If I set this to performance here and we run RTCQS, we can see that now CPU frequency scaling is okay. Several other warnings that I've chosen to ignore. It's handy for validating the performance implications of the configuration that you're running. Another thing I've done is set up a program named XRunCounter. This piece of software tries to generate enough load to produce an XRun, and as I mentioned before, XRuns happen when your operating system really just can't supply your audio software with data fast enough to please it. XRunCounter is not part of Nix packages, so I had to package it up separately, making a custom derivation of it. There will be a link from the Talkie script, which I'm using to read from for this video, that will include a link to my configuration, which will include this derivation in case you want to reproduce it. Once it's installed, you just run XRunCounter-S, which is a stress test. One of the things that it complains about here is that it can't find PACTL, which is part of Pulse Audio. That's normal because we're not using Pulse Audio, we're using PipeWire here. The test underneath of it where it says test 6 core, that's where it's actually testing jack. It is exercising PipeWire's jack emulation. The purpose of this thing is to let it go long enough to get some sense of when X runs start to happen. Okay, that took about a minute or two to generate the first X run. It tells me that the first X runs happens at DSP load 105% in cycle 72681. This is not particularly useful to me except relative to other settings that I use. So currently I have a PipeWire quantum size of 64 and a jack buffer size of 64. If I change those values and I rerun XRunCounter and I get something different, something sooner in an earlier cycle, it means that I probably need to change something, either make a buffer bigger or smaller. In my first video in the series, I used a real-time kernel by enabling the musenix.realtime.enable flag in my configuration. Since then, I've removed that because some software that I want to work on this system works on a non-real-time kernel, but does not work on a real-time kernel. I use the system for general purpose tasks. But what I have done is set up musenix.rtirq, which starts a service, a systemd service at boot time, which does some IRQ magic that I don't fully understand. I think I have some gist that it prioritizes the servicing of IRQs associated with certain devices, like your audio card, before other ones. And I think to get the best effect from this, I would need to go in and configure it further than what I've done. I've just turned on IRQ enable equal true, and that actually starts the service. But I think I would need to point it at my audio device, or perhaps the timers associated with my audio device, to have it do the best job it possibly could. I haven't figured out how to do that yet, or even whether I need to do that or not. It doesn't seem to hurt anything, and from what I've read anyway, just enabling it in its default configuration can be helpful. We can see that RTIRQ is running by using systemctl status rtirq.service. Making sure I got the system configured to the satisfaction of RTCQS and running XRunCounter and setting up this RTIRQ stuff. Even without a real-time kernel, we're done to reduce the chance of XRuns. But in reality, there's so many knobs to turn, some that we haven't even talked about yet, that might affect this, that I can't really tell you with any confidence whether they've had an effect for good or bad. In reality, I think I'm going to have to use this thing for a while longer to see which knobs are best turned and which are left best alone. But I think at very least, I don't think I've hurt anything by turning the knobs that I've turned so far. So we'll move on to real-time monitoring latency. Human psychoacoustics are such that two distinct but similar sounds can't reliably be distinguished apart if they're within somewhere between 10 and 20 milliseconds of each other. The sound of our voice or our guitar pluck is picked up by our microphone or our guitar pickup, and then subsequently processed by our audio software. And if we have monitoring on, it's fed back into our ears via our monitoring headphones, particularly when using audio processing software like effects stacks like Guitarix or something like that. We want the sound we make to get into our mic or our pickup through our computer rig, processed by our software and our plugins, and out of our headphones and into our ears within this number of milliseconds, this magic number of 10 to 20 milliseconds, more like 10. Otherwise, we'll hear both the original sound and the monitored sound phase slightly or totally out of sync, which will effectively destroy our ability to concentrate on the instrument that we're monitoring. This isn't really an issue with straight up recording. We're not listening back to the process input in real time. It's only a problem when we want to monitor it, when we're actually making the noises. Get that metal effect on your guitar. If it's too far out of sync and you play a chord on your guitar and it takes half a second to come back, that's going to be very disorienting. So we need to take steps to try to reduce the real-time monitoring latency. So to start, we need to do some fooling around with hardware settings. We need to mess around with ALSA. It is the lowest level interface to sound offered up by Linux. We need to determine the lowest possible settings that we can use for the ALSA period size and period number that purports to give us a round-trip latency for some test pattern sound without any processing or effects that is at least below 20 milliseconds and ideally below 10 milliseconds. And the piece of software that we can use to do this is called ALSA Delay. Note that it's important that we don't have any ALSA configurations from default before we do this. If we do, we'll get misleading numbers. Essentially, if you've done any messing around with your ALSA configuration and these things sound familiar to you, undo those before doing this. To get ready for this, and just to have sort of a baseline place to start from, I'm going to muck around with some switches on the back of my sound card to set it to a sample rate of 48 kilohertz. Doesn't really matter. This is just arbitrary. You could set it to whatever you like. I'm using 48 kilohertz because it tends to be what phones and other sort of consumer devices record at, and it's just convenient to have the sample rate of the recordings I make locally match the sample rate of recordings made on my phone. I'm then going to connect a cable from each of my sound card inputs to each of my sound card outputs, which is required by this ALSA delay program. This is an Edirol UA25, and in order to put it in 48K mode, I need to set the advance on and set it to 48K, like that. If I don't have the advance on, it's always 44.1. And then in order to loop the output to the input. Let's do that. I think we're set up to run also delay. We have the cables connected from the output of my sound card to its inputs. And I've shut down all other sound software on the system, including Ardour, Audacity, the normal end-user applications. I probably should shut down PipeWire as well. It is not necessary for this test. I haven't because I happen to know that it doesn't matter in my setup. But if you run this command, which is going to give us an integer number that we're going to use in a subsequent step, and you do not see your device, I see my device, which is UA25 here, card 1. If you don't see your device when you run, shut down all your audio software and shut down PipeWire. It is card number 1. I'm going to remember that fact. At this point, I want to put the also delay program on my path so that I can run it. In order to do that, I'm going to use Nix shell -p zeta also PCMI. It's now on my path. I'm going to run also delay successively with different arguments. What I'm trying to do is find the set of numbers, the set of arguments to pass to also delay that imply the lowest round trip latency that I can achieve without pops, clicks, or other weirdness happening on the audio channel. So the first number that I'm going to try, I happen to know that that this device can handle it well, because I've done this several times now, is 28311. The arguments here to also delay are the device number prefixed with HW colon. So also delay HW colon 1 means my UA25 device is the input device. HW colon number 1 means UA25 is the output device. We're going from the same device into the same device. Third argument is the sample rate, which my device is set up for, which is correct. It is 48,000. Fourth argument is the ALSA buffer size. This will either be 128, 64, or 32. Fifth argument is the ALSA period size. It will either be 3 or 2. Sixth and seventh arguments are the channels of the device that accept the sound that we're using to measure the latency and produce the sound that will measure the latency, and they happen to be 1 and 1 in my case. If it's not working for you, you see something strange like it can't find the signal or whatever, just change the 1 to 2. So we're going to start here, and then I'm going to successively reduce the ALSA buffer size and reduce the ALSA period number over the course of several invocations of this command to find the optimum buffer size and period number. Here we go. Okay, we can see that that's 20 milliseconds. We just need to let it run for a little while, see that there's no weirdness happening. Okay, so that seemed to be okay. We let it run for a while, maybe a screen full. And now I'm going to go down to 128 and 2. I think when I change the 3 to a 2 there, I think what's happening is that the amount of data that is put into a single clock cycle is more. I'm not entirely sure about that, but that's the mental model that I have about what's happening here. So when we reduce the period number, it goes faster. So I'm going to press enter here. Okay, that's working. And we can see that the latency is slightly lower. It is around 15 milliseconds or 14 and a half milliseconds. Let it go a little bit longer. Okay, doesn't seem to be any weirdness. It's good. 64, 3, 1, 1. Oh, no, 64. 64, 3, 1. And see if we get weirdness or see if it works. That is weirdness. Certainly weirdness. That is not working. How about 64, 2, 1, 1? I think everything down from here will not work anymore. Nope, too small. And 64. Go to 32, 3, 1, 1. Can't even open the device. 32, 2, 1, 1. Yep, can't open the device. So it appears that the optimum setting for our device is 128 buffer size and 2 period number. And that gives us a latency of 14.5 milliseconds. Now, I don't know if you've noticed or not, you may not have noticed, but during the recording of this video, you might have heard a few sort of pops and clicks in various places that don't sound like they're coming from my mouth. You'd be correct. I recorded the beginning of this video up until everything you've heard on the device that I'm doing this testing on, in a mode where I had the device set up to do a buffer size of 64 and a period size of 3. And I believe that it was causing audible clicks. So I couldn't, I think it might be because I am really, just scraping the limits of this system in a certain configuration. It may be that if I ran RTCQS, it might be that, my CPU frequency scaling is getting in the way here. But in reality, I don't want to be that close to the edge, because when it doesn't work and when there are pops and clicks, the difference between, let's say 12 milliseconds and 16 milliseconds is not beneficial enough for the pain of forgetting about this and having to troubleshoot it every time. So I'm going to leave it at 128 and 2 and just call that the best I can do. The next step is to use Ardour to figure out how much of that latency is due to the hardware, the DACs in my sound card, and the computer hardware itself, as opposed to the rest of the chain. This is known as systemic latency. Linux software can do some recording time compensation for systemic latency. Apparently, it's most noticeable for punch-ins if we set it properly. If we use Ardour, open it up, go to Audio MIDI Setup, also Audio System, choose the right device, set the period size and number we found in the last step as the buffer size and periods, respectively. Go to Advanced Setting, Calibrate Audio, and click Measure. Mine is 969 samples with a 14.5 millisecond round-trip latency and a systemic latency of 440 samples at 9.16 milliseconds. Ooh, we care about the number of systemic latency samples for the next step. So if you're conservative, you can also click Use Results and try to record an audio track. Make sure it works and there's no audio artifacting. If there's artifacting inside Ardour, re-record, working your way back up the pairings of period size and number from the also delay step above until there isn't any. The settings that produce no artifacting are your actual lowest settings for the period size and number. Whew. I'm not going to do that because I already know where the boundaries are of what this system can handle. Now that I've figured out the optimum period size and period number and some value for the systemic latency, let's see whether we can make our actual life better. The first thing I'd like to try out is setting up Audacity such that we can do monitoring of its output in real time without using the numbers we just got to configure PipeWire's jack emulation. We'll run Ardour without any configuration changes and just sort of listen in on the real-time monitoring latency. To do this, I'm going to start up Ardour and just configure things such that I can hear myself, which is true at the moment. The end result is that it is really annoying. I can hear myself coming back about, I don't know, quarter of a second or maybe a little bit less than that through the headphones. It's just totally distracting. I'm going to turn on audio monitoring, hardware audio monitoring on my device, which I will record, and so you get some sense of the phasing of the things. Audio monitoring is now on. You sort of hear that between the hardware and the software latency, there's some phasing happening, which is always going to be true. It should get better once we configure things. So let's do that. Okay, that is much better, much less phasing. I will show you what I did in a second, but before I do that, let me turn on the hardware monitoring switch here. There's still going to be some phasing, but it should be better. Yep, there we go. There's the phasing, and it is no longer a quarter of a second or so. It's just a few milliseconds behind. Yeah, it kind of sounds like you're in a tin can when you have both the hardware and the software monitoring on, but if you have just one or the other on, it's hard to tell the difference. So now that I've taken a listen to the sort of default monitoring latency of the stack, I'd like to now try to plug in some of the numbers that we gleaned from using also delay and Ardour into something called Wire Plumber. In case you didn't notice, this is pretty complicated. But Wire Plumber is a piece of software that accompanies PipeWire, that its job in life is to notice when sound hardware is plugged into the computer. And when it's plugged into the computer, it then configures some stuff about PipeWire that's related to the device that's been plugged in. In our case, we'd like to create a file that when our device is plugged in, when my UA25 device is plugged in via USB to this computer, that it will notice, and it will set the ALSA period number, which we found via ALSA delay, to 2, and the ALSA period size, aka the buffer size, to 128. And we'd like to set the latency internal rate to 440. So let's change our file, or let's change our Nix stuff such that that file gets created. In order to do that, we are creating a file inside of environment, etc, wireplumber, main.lua.d / and then a Lua file name. Its job in life is to say, when something is plugged in that is an either-all UA25, both on the sink and the source side, apply these properties, where the properties are latency internal rate, which was a systemic latency that we got from Arter, API also period size 128, API also period number 2, and then I have this hair here which is disabled. This is actually a comment, this dash here I'm playing around with, this disable batch thing. Pay no attention to that. Once we have that in place, we can run sudo NixOS rebuild switch, and that file will be put into our etc wireplumber main luad directory, and should be picked up by the system. I've already done that, so I'm not going to run that right now, but that's what you'd have to do to get it enabled. Once that is run, we actually have to restart. This doesn't happen by default automatically. Restart wireplumber and PipeWire in order for those changes in that Lua file to get picked up. So those changes should be picked up now. I had to restart my OBS. And now we can start to test Jack out. So far, we've just been testing ALSA, and Jack is the way that we want to talk from our software through PipeWire to our hardware. So now we can get a sense of the latency that some programs that use Jack think we have. One of those programs is called Jack IO delay. In order to get Jack IO delay on your path, you can run this Nix shell pjack example tools like that. At this point, Jack IO delay will be on the path. And then we can run Jack IO delay, like so. And it will just keep looping there. In order to actually make it have an effect, we have to do some Jack configuration. I'm going to use qjackctl to do that. This is the program that lets us map inputs and outputs inside of Jack. The first thing I'm going to do is connect the sound card's capture device to the in of the Jack delay program. And the second thing I'm going to do is connect the Jack delays out to the playback of the sound card. Now, this is going to make a horrific noise. You have been warned. Please pull off your headphones now and think in 10 seconds, 5 seconds. I'll give you 5. 5, 4, 3, 2, 1. Okay, so that was horrific noise. Sorry about that. But now we see something slightly different in the output of. I forget where I am in the script. This is so complicated that I've forgotten where I am in the script. I'll be glad when this video's over. Anyway, I don't know if I've told you about this before, but if I haven't, here we are. This is Jack IO delay. You like it? Me too. It's telling us that we have 8.5 milliseconds total round trip latency, but it's giving us this number that is kind of absurd for extra loopback latency. Extra loopback latency is the same thing as systemic latency. Did you know that? I didn't know that until I started this. Now I know that. I'm getting a little loopy making this video. All right. So The reason it is telling us that is because we have already configured it with the wrong, for Jack anyway, with the wrong systemic latency. We would like to configure it with something else. In order to figure out what that something else is, I'm going to change the internal latency, or I'm going to disable the internal latency rate here. I'm going to rebuild the system. Are you with me? Are you with me? Here we go. Rebuilding. A rebuild, sudo NixOS rebuild switch. Good times, good times. We've reconfigured our wire plumber Lua file without latency and internal rate. Now we need to restart. And now we can run Jack IO delay again after restarting PipeWire and wire plumber. Okay, again, gonna be some noise. I'm gonna tell you in 5, 4, 3, 2, 1. Take your headphones off. Oh no. This extra loopback latency here, we had it as 440. I put 400 here, but I meant 440. That's what Arter told us it was. It's not, at least for Jack. It is 154. But in reality, it wants half of that. And I'm going to type it in here. It is 77. Back-end arguments INO. Once we do that and we rebuild, I'm going to rebuild. I'm getting super loopy here, man. No one is listening to this video, I'm sure. This is ridiculous. Okay, it is reconfigured. And now I need to restart PipeWire and wire plumber. But first I need to shut down OBS and start it again so that I can actually record things. I will be right back. Now I need to start QJack Cuddle again. I need to start Jack IO delay. And again, some noise. I'm sorry. Going to do it one more time. 5, 4, 3, 2, 1. Okay, there we go. Now our extra loopback latency, which is our systemic latency, quote unquote, is now 0 frames because our latency internal rate is making amends for us in the configuration of wire plumber, which is passed on to PipeWire. Got it? Got it? Good. Excellent. Excellent. So that is the vast majority configuration we need to do. There is one other thing that we can do to potentially make things slightly better that doesn't seem to have much impact in the real world, but I'm going to change the Jack quantum size, the default quantum size. It's quantum, it's a quantum. Sure. It's a buffer size of some kind. And I'm going to change it both for PipeWire itself, which is the default clock quantum, and default clock min quantum, we do the default clock max quantum, set them all to 128. I'm going to change it for PipeWire's Jack emulation node quantum. And that means it's 128 at 48 kilohertz. And once we do that, as I mentioned, it doesn't really have much effect. It slightly, I can't really tell the difference, to be honest with you, when I do it. Right. I think that is about, I think that's about all I can take. I think what we've learned today is that I've reached my limit of patience of messing with this, and this is going to have to do. It's going to have to be good enough. I hope it stays finished, because this is extremely complicated. The Mac people are just crying laughing right now. But anyway, I appreciate you guys watching. I hope this helped somebody somewhere. I doubt it highly. Please, if anyone got anything out of this, please leave a comment. I don't think it's possible. Anyway, all right. Thanks for watching. Bye-bye.